So, we look at analysis of organics in water. So, the first thing is the extraction. We will look about extraction. Extraction means we are talking about something which is at very low levels. So, typically we are talking about nanogram per liter or micrograms per liter, that level of concentration. So, we want to pull it out. So, as if you recall, the objectives of extraction are use of compatible solvent, so exchange of A to compatible solvent matrix. This compatible means with to the instrument. Second, it gives you an opportunity to concentrate the sample. So, you can do this in multiple ways. So, one of the common methods in which people do this is is you have water sample, which contains A, they add another solvent which is a liquid, another liquid, and then A will transfer to this. So, this is directly using what is called as liquid extraction. So, the second solvent liquid that we use, by definition, if you are going to do liquid extraction, it must be immiscible in water predominantly. So, you use an immiscible, when we say immiscible, we are not talking it from environmental point of view, all of them have some solubility, but bulk solubility is very small. So, that if you add to 1 liter of water, if you add 100 ml or 50 ml of solvent, you can recover most of it, 40 ml you can recover at least. So, we did that calculation last time. So, this is one of the reasons you can only recover some of it, you can't recover all of it because some of it may have already dissolved in it. So, that is possible, we do not worry about that, our goal is to extract as much as possible. So, typically immiscible solvent which can now has a greater solubility of A in it. Okay. So, if some organic solvent that can hold A in a larger quantity. So, typical extraction solvents are hexane, dichloromethane. These are two very commonly used. You also use isooctane and things like that, but typically these two, most of the methods you will see these two. Dichloromethane is CH2Cl2, yeah, this is C6H14. This is a very hazardous compound, dichloromethane. So, it is a chlorinated organic solvent. But it is one of the strongest solvents that there is. Okay. Many of the chlorinated solvents, organic solvents are very powerful. They will extract a lot of things. Okay. But they also are listed among the if you go and look at the priority chemicals of concern organic, you will find some of them there. You will find some of them there because they are used in large quantities. So, there is opportunity of exposure is very high. So, in industry and all, people use solvents for all kind of things. They are used for painting, cleaning of things, it is used because it is an extract, very good extract. So, you want to clean something, it will come out very easily. Yeah. So, for this kind of extraction, we are not using large quantity, we are using small quantities, and that is why you have a section in your analysis method which is called waste management, which means you will end up at the end of your extraction, you will have some dichloromethane or hexane, which is not supposed to, you can't throw it down the drain. You have to dispose it properly. Okay. So, this is one point in which you have to do method selection properly. So, there is a waste management associated with it because you are introducing some hazardous chemical here, So, you have to understand this principle when you are, we are not discussing it in this course, but when you are discussing treatment processes or remediation, you have to remember this, that maybe sometimes it is very effective to use some chemical for treatment or cleanup, but then that you are creating more problems, environmental problems by this. But here the usage is so small, the quantities are very small and the purpose is to analyze. So, you see it is not considered as we will search for methods which are more sustainable, but if it is not, it is not. So, we do whatever is the best available for us. Okay. So, we extract, when you extract water as it is, raw water, sometimes you will get everything, you will get all the interferences in your sample, and this is true mostly for samples that are coming from say wastewater treatment plants or sewage treatment plants or some such thing. You want to know what is the concentration there. You may find some other material there and that may also get extracted, and that will introduce interferences. One example is this. So, when normally say I collect a sample of water from a very turbid lake, I do not do anything, I just add hexane or dichloromethane and extract. It will extract everything, it will extract from the organic carbon, there will be organic carbon in the water, it will extract all of that. So, if the original water contains A plus organic carbon plus some other solids, say let us not call it A, we will call it as bunch of AI, we will call it as AI, which means there are lots of chemicals. It is not only extracting this AI from water, it is also extracting water from OC and from the solids. And this AI will contain a few things. So, here comes the definition of an interference, very interesting now, because if your goal is to find out what is there in the water, whatever is there in the water is going to come out. So, none of it is really an interference. So, the interference is very specifically defined for one analyte or a group of analytes that you are focusing on. For example, if I have PAHs plus oil plus some other thing, say let us say metals in the water, I am interested to know all of this, right, how much of PAHs are there, not how much of oil is there. But if I am analyzing PAHs specifically, these two may interfere with my analysis of pH. The oil and the metals will interfere. So, in my method for analysis of PAHs, if this is seen as an interference, these are interference. So, I must do something with these two before I go on with the analysis of PAHs. So, you have to interpret the interference like that. So, there is no absolute interference, interference is relative to whatever you are trying to analyze. All of these are important for analysis. So, the other interference is from what we talked about last class. When I am analyzing water, I want concentration of A in water alone. If this is associated with solids, and I am really not, I am getting the wrong information. Yeah. So, before this you have to, before you do liquid extraction, if you do not want that information, you have to filter the samples. So, filtration must be done before LLE. Okay. So, normal sequence of events that you will see is when the sample is collected, then we move on from, like, after this we do the next step. Okay. I want to sidestep a little bit here and talk about filtration a little bit. So, we have discussed something called as total suspended solids. I think we have not discussed it in detail, so it is a good place to do this now. When you say total suspended solids, it is we are taking a water sample and filtering it through, we are putting a filter paper and all the solids are trapped on here and you get water, and then the mass of filter that is collected here divided by the volume of water will give you rho 32. This is total suspended solids, rho 32. Yeah. There is one piece of information that is needed here is the what is the filter paper that we use. Have we discussed this in the class? No, I do not think so. What filter paper will you use? So, if you go and open a catalog for filter papers, you will find a lot of filter papers. You have used filter papers from my school for various things. What is the definition of the filter paper that we use here? What kind of filter paper do we use? What is the characteristic of filter papers typically when you say filter paper? What you say pore size. Predominantly you say pore size. So, pore size is in some say in microns. So, it will say 10 microns or it will say 1 micron. You can go up to 0.4 microns, 0.2 microns, 0.1 microns, all of them are there. Different kinds of filter paper. Up to about 0.7 or 0.4 microns, up to about 0.7 microns, you have glass fiber filters. From somewhere around here, you have membrane filters, and you have more specialized filters. Okay. So, you have a wide selection of filter paper and filter materials. What will you use? Is there a qualitative rational decision why you may want to use? What is the people who have done filtration will know what is the difference. What is your objective? What is your objective? We had all this example analysis problems because for this question. What is your objective in doing this? In analyzing TSS? Objective is what? Very simple answer. Objective is separation of solids. Okay. So, what are the solid sizes from what that you would like to separate? What would you like to separate? Based on the example that in the last week that we gave, mainly what would you like to separate? If you are doing organic analysis, what would you like to separate? If I am analyzing an organic chemical in the water, I would like to separate some component which will accumulate a lot of organic compounds. So, mainly I am interested in separating organic carbon for that purpose. But TSS does not differentiate between organic carbon and all that. TSS is suspended solids, it does not care. So, it is anything, all particles from whatever size down to whatever size. Okay. So, ideally what would I want to use? If I have filter papers available for 0.1 pore size, can I use 0.1 pore size? It will stop everything 0.1 because colloids, organic carbon is in the size range of 0.4, 0.2. I will definitely remove all of them. Yeah. Yeah. Then why do you have filter papers of 1 micron and 4 microns and 10 microns? For one, it's easier to make. That's one reason. But they're still there in the market, and people sell it for one reason. So what is the other? As the pore size goes down, what is the other consequence in filtration?
It takes longer.
It takes longer. It takes enormous amount of pressure drop to push liquid through solid that filter. So it takes very long to do this. Second, so let us say I use a filter, say I use 1 micron glass fiber filter. I am able to do it in filtration of 1 liter in 5 minutes. Yeah. I take 0.7 micron filter, it takes 1 liter, I am able to do it in 20 minutes, or sometimes depending on the amount of solids that is present, I may not even be able to finish it. Filter will get clogged, I can't do. So, the way we do filtration here, if I want to do filtration, if I just put it on a filter paper and leave it, the pressure drop across the filter paper itself is so much that the moment the first drop of particles come and collect there, it will not go through by gravity. So, you have to put some negative pressure here. So, you have to apply a vacuum to do this. You have to, otherwise by gravity alone it will not happen. You have to push, you have to have a vacuum pump to pull the water across the filter. There is a pressure drop that is acting here. So, you have to push it across that using the filter. So, even with the vacuum pump you will not be able to filter it sometimes with 0.7 micron filter. So, between 1 and 0.7, if there is this much difference, I would rather use a 1 micron filter. What will be my loss of information if I use a 1 micron filter versus 0.7? So, let us say that some small particles will get through, will go through. For 1 micron pore size does not mean all particles below 1 micron will not get filtered. That is not true. It's filtration theory, it is not the pore size, it's a lot of, it's much more complicated. So, you will get retention of particles much lower than 1 micron, but there may be other particles which will still go down. That is one of the basis for which we use 1 micron filters instead of 0.7, because it is not really needed. 0.7, 1 micron is probably good enough to do whatever colloid removal you want. But still there is a question, one has to draw a line somewhere, and the basis for that is not, one of this is this, that if filtration was very easy with 0.5, people would use 0.5, but filtration is not easy, and so 1 micron filter okay. So, 1 micron filter is used. What is the difference between 1 and 0.7 in terms of information lost? Anybody? What is TSS? How is the analysis done? How is M3? How do you get M3? By weighing. It is a gravimetric measurement. So, gravimetry, if I take particles that are 1 micron versus particles that are 2 micron versus particles that are 0.7 micron, 0.5 microns, and let us say there are 10 raised to 6 particles. You calculate what is the mass contribution of this one, this one and this one. You can calculate if you want. So, take density of the particle as say 2000 kilograms per meter cubed or 2 grams per centimeter cubed. It will turn out that even if you have 1,000,000 particles, the contribution to mass is very small. You will not even probably see it in the balance that you are using. The 4-digit balance that you use, you may not even see it in terms of contribution to mass. So, while it gives you lot of separation, little more separation, 1 micron filter will give you 1.7 and below, these filters will give you a lot more separation than 1 micron filter. The information that you get from terms of mass gravimetry is decreasing, it is almost negligible while you do this. You can do the calculation for yourself, convince yourself how much is the loss. So, since the total suspended solid methodology is based on gravimetry, it does not really matter. This above below 1 micron, you are not going to get any additional information, and you are also going to you are going to waste your time by trying to push it through the thing, and you are not getting any additional information. So, 1 micron is set as the standard filter size for TSS. So, because it is TSS standard filter size, when you do water analysis, you generally do TSS analysis, which means you are filtering the sample, and that filtered sample is what we usually take for analysis of water. Now, it does not mean that the water that is filtered through 1 meter may contain colloids which have organic. For that, you have to measure the TOC and then correct that value. That is a separate issue. Okay. There is nothing you can do about it in terms of separating, but you can at least calculate the TOC and say, I know the total concentration, now I know the TOC, I want to find out what is the actual aqueous phase concentration based on the calculations we did in the last week. Okay.